You have wireless stuff.
Oh, thanks. This one's yours. You bet.
All right, let me do this from here. Okay, so our next speaker is Aaron Turon. Aaron got his PhD at Northeastern, and I actually know him very well from then. I was on his committee. So Aaron's going to be talking today about Rust. He's been working at Mozilla Research, and he's going to be talking about Rust and PL research in industry.
Thanks, Amal, and thanks, Kathleen. Cool. Okay. So yeah. So I got the invitation to give this talk from Robbie, and it specifically talked about sort of talking about PL research and industry. And probably you guys don't know Robbie very well yet, but I do. And the way that I interpreted this is an invitation to corrupt the youth. So challenge accepted. So yeah, so I thought a bit about how to frame this talk, how to sort of share some of the lessons that I've learned transitioning sort of out of an academic research setting into a more industrial setting. And so one way of framing this is, oh, it's the ivory tower versus the Googleplex. I don't work at Google, but I think the Googleplex is a good representation of evil industry stealing all of our PhDs, right? But actually, I mean, there's really a wide variety of research that takes place in both academia and industry. So I think actually this is not such an interesting framing. I think the more interesting framing for today is talking about theory versus practice. And I've done a fair amount of both sides of this in my career. I have great affection sort of for both sides, but today I'm going to sort of argue from the practical direction and try to share some of my perspective from Mozilla. Right. So, I suspect you all are coming from pretty different backgrounds, but I can say for sure that you are going to be learning a lot about some very important theoretical tools starting today. In fact, the next talk. And so just I wanted to list a few of these here, some of the tools of the trade, right? So we have things like the lambda calculus or lambda calculi, because we often invent new lambda calculi. We have operational semantics as a way of understanding what the meaning of programs is. We have typing rules. We have different ways of doing soundness proofs and so on. These are all concepts you'll get familiar with. But these are all fairly theoretical tools, which we use to sort of do our work and communicate. Now, at the sort of foundation of these tools is the idea of a model, right? So languages, sort of in the real world, like I'll be talking about, are very big artifacts. They're too much to sort of study directly most of the time. So when we're interested in some particular feature, what we generally do is make a model of a small toy language, like one of these calculi, that sort of boils away everything else except for the feature we really want to focus on. Right, so maybe we want to understand what classes mean in a language, right? And so we might actually try to understand them in terms of something else, in terms of some more primitive components, and we might use a model to do that. Another thing that models do is they tend to emphasize something we call orthogonality. So the idea that basically instead of having very large features that couple together a lot of different ideas, you want to sort of boil things down to different features that work independently and then can be combined to give you results. And these kinds of models that we work with are very good at getting at that kind of orthogonality. Another really important role of models is being able to do proofs, being able to make the math tractable, right? So this, again, often comes down to size, right? You have something bite-size, a piece of math that you can actually sit down and do a proof, pencil and paper, or maybe in an automated way. But it's much more possible to do this with a small model than with a big language. And then finally, I think a really important role of models is as a way of communicating to other people, right? So it's hard to be precise with just English prose or some natural language. These models give us a way to be extremely precise about what we're saying, so that we can do mathematical proofs, but also so that we can be very clear when we're talking to other people. But as I'll come back to later, this is true when you're communicating with academics, less true in industry. Okay, right. So those are some of the good aspects of the theoretical tools that you all will be learning about. But from a more practical perspective, where do these tools fall short? So these bullets are basically some of the points I'm going to make over the course of the talk through a few different stories about Rust. The first one is that the models, they're all about boiling things away. In fact, that is the whole point, right? That you're getting down to the essence of some idea or some feature. And that's really great for building an understanding. But if you're trying to build a real language, all those details that you just swept under the rug actually matter. They matter to people. They matter to making the language usable and successful. And so you want to be careful, right, that you don't get sucked into this thinking that the model is the only thing that matters, that syntax is not important, right, that surface details don't matter to people. They're actually some of the most important work that we do in industry on languages. I mentioned orthogonality before, and I think a lot of us in this field take orthogonality as a really important design principle, but it's not always what you want, and I'll talk about that more later. And then I'm going to touch on some concerns that just don't really come up when we're talking about models, but end up being actually really important in practice with languages. And finally, I'll just mention this right here on this slide. So I sort of already alluded to the fact that models are good for communicating to people in the know, people who are academics. But one of the things I was really struck by in moving to doing this kind of research in industry is there are so many people out there who are very interested to take the ideas that PL researchers are producing and do things with those ideas. But they get stuck, right? The moment they see some lambda calculus notation, it's hopeless. They can't make sense of the paper, even though they're perfectly capable of understanding the ideas. The notation actually stands in the way. And so this is just something to keep in mind. I mean, I remember as an academic, we often ask the question, like, why aren't people in industry taking up our ideas more often? Why does it take so long? And I think this is actually one of the things that stands in the way. It's something we take so for granted because every paper is written in these terms, but I think we should take more opportunities to translate our ideas to a way that can be understood by people in industry. Okay, so that's the overview for the talk. So let me talk a little bit about Rust, which is the language I'm working on. So first of all, I don't know, probably most of you know what Mozilla is, but you might be curious as to why they're in the language business. So Mozilla, of course, makes the Firefox web browser, which I hope you all use. And browsers are a pretty interesting kind of application. On the one hand, as Mozilla knows very well, browsers compete on performance, right? This is why Chrome has been ascendant, right? Because it has had much better performance than Firefox. And to reach the kind of performance you need to be competitive, you need really low-level control over the machine, right? You need absolute performance. You need the language not to stand in your way. And that's why all major browsers are written in C++. Okay. On the other hand, browsers are the gateway between your machine and an internet full of hackers that want to break into it, right? And so safety is also really important for browsers. But there's a pretty interesting tension here because if you know anything about C++, you know that it's not a safe language. It has all kinds of holes, and you get security updates from browsers all the time because people are finding these holes, finding ways that people can exploit your browsers, all because it's written in an unsafe language like C++, right? So how do we thread the needle? So that's where Rust comes in. So the idea of Rust is to provide a safe systems language. So a language that can credibly compete with C++ in terms of giving you low-level control, being a systems-level language, but guarantee safety. And I'll talk a little bit later what exactly I mean by safety. But most languages that you're likely to be studying or thinking about are sort of safe out of the box. They are memory safe in particular, right? And so Rust is developed sort of hand in hand with a new browser engine called Servo, and that's kind of cool. It's a lot of languages take a while to find a sort of killer app, which often has a role in defining the character of the language. Rust kind of came with a killer app as a sibling, right? So that's pretty nice. Okay, and I should mention, so I joined Mozilla a couple years ago. I now manage the Rust team, and we're kind of a mix of academics and engineers, right? So we have several PhDs on the team, but also several people who've come through a more engineering track, and I think that blend is really interesting. So Rust takes ideas from a lot of different languages. I already mentioned C and C++ as being important in terms of what we want to do. The Cyclone project is something very interesting in this space. I would encourage you to look up papers on Cyclone. Definitely, so Cyclone was also trying to be a safe systems programming, the same safe systems language, the same way Rust is, and Rust borrows a lot of ideas from it. But you can also see a lot of ML and Haskell and other functional languages in Rust. Cool. So that's Rust. So now I want to tell you a few stories about Rust and relate them back to these points about theory versus practice. So the first topic is ownership, which is probably the defining concept of Rust. So I'm going to start with some C++ code. If you're like me, when I started on the Rust team, you hadn't seen C++ in a while. That's OK. So in particular, I'm going to walk through the kind of unsafety that's very easy to get in a language like C++, and that leads to exploits in a browser. Okay, so here we have some simple code, which has a vector, does some work to actually add some elements to the vector or something, right, with the dots, and then it's going to take a reference into that vector. Now, the details of the layout here are not too important, but basically, on the left side of the screen, you have the stack. That's where the metadata about the vector lives. And then the data itself lives on the heap. So you have a pointer data going to the actual contents of the vector. OK, so the first thing we're going to do is take a reference into the contents of the vector. Right, so this is a pointer. This is a kind of pointer in C++. And so now we have data pointing to that first element, and we also have lm pointing to it. Meanwhile, we push onto the vector. Okay, but we originally only allocated one slot for the vector. So to add to it, we're going to have to allocate some new storage, copy over the contents, and then push a new element on. Okay, so when we do this, the data pointer swings to this new memory location where we've done that allocation, and we deallocate the original buffer. And of course, now the problem is this lm pointer is still hanging around. And so if we go ahead and try to output its contents, we're going to get, well, if we're lucky, a crash. But if we're less lucky, something that a hacker can use to take over the machine. Right? OK. So that's bad. That's the kind of safety problem we'd like to prevent. And I want to just take a moment to analyze what it is that led to the unsafety here. So on the one hand, we had aliasing. So we had two different pointers pointing to the same location. That was ingredient one. On the other hand, we had mutation, right? So we went through one of these aliases, and we actually mutated its contents. In particular, we freed the buffer, and we did so without regard to the other aliases that might be around. So it's this combination of mutation and aliasing that gets you into trouble. And that's just that alone is something worth knowing and thinking about. A lot of research in functional programming and in PL in general comes down to managing mutation and aliasing in one way or another. It's a very interesting field. OK, cool. So mutation and aliasing together are a recipe for disaster. So we want to prevent them from being combined. There are many, many ways to do this. A lot of research here starts by, or at least one line of research, I should say, starts by ruling out aliasing altogether. So you can mutate, but somehow we prevent you from aliasing. And so in particular, there's something called substructural typing. And you may hear the terms linear typing, which is a particular kind of substructural typing. But anyway, the key idea there is that when you mention the name of something, you're sort of consuming that value under the hood. So it's not possible to have multiple names pointing to the same object, because basically when you create a new name, you've lost the ability to use the old one. And I have a quote here from a really good guide to substructural type systems. This is from the book Advanced Types in Programming Languages. And it says, talking about some research in this area, in each of these cases, the authors do not stick to pure linear types, which are things that just totally rule out aliasing. Instead, they add coercions to the language to allow linear typed objects to be temporarily aliased in certain contexts, yada, yada. Okay, and that's really the most interesting thing that Rust does. So there's lots of different ways to do this, and figuring this out for Rust was really the thing that clinched the language design. So let me talk for just a couple minutes about how Rust manages this kind of aliasing. So we have something called borrowing. And the idea is that you get a temporary ability to alias. And the type system sort of knows that this aliasing is going on, and it's going to prevent mutation during that aliasing, and then it knows when it ends. And so in particular, there are two kinds of borrowing. There's the ability to make a shared reference, which is where you get aliasing. When you do that, you give up the ability to mutate. And there's also the ability to do a mutable borrow, which doesn't allow aliasing, but still allows for mutation. So let me show you some examples. So here we have something sort of similar to the C++ code I wrote. This is Rust. So we are creating a new vector, right? And that basically has the same layout as before. We're pushing two elements onto it. And now we can call this function use, and we're going to pass in a reference to the vector. And so this type &vec means a shared reference. So here's the interesting thing, right? So we're sort of loaning out access to this vec. And in fact, we can make multiple loans at the same time. We can make aliases. And when we do that, we get a pointer. So this is all feeling very similar to what we saw in the C++ code before. So why don't we get into trouble? Right. Sorry, skip through this for a second. So the reason we don't get into trouble is that these shared references are immutable. So I didn't show you what the use function was doing, but if we tried to actually mutate the vector in some way, the compiler would prevent it, right? So whether we were trying to push something onto it, whether we were trying to mutate some particular element, in either case, the compiler is going to catch this and say, you can't mutate a shared reference, right? And so that's part of the way you're getting, basically you can have either the ability to make aliases or mutate, but not both at the same time. Okay, so that's the rough idea. The details here aren't super important. I'm happy to talk offline in more depth. But now I want to sort of start talking about the theory versus practice distinction, right? So a lot of these ideas that Rust is using have some basis in earlier theoretical work. These kinds of ideas are probably familiar to the more senior people in the room. But a lot of the important work to actually make this work smoothly in practice lives at the surface. So let me show you what I mean by that. So I gave a function earlier, use, and I wrote a signature like this for use, right? So it's taking a vec, a shared reference to a vec, right? And I didn't mention this before in the earlier slide, but actually these references are parameterized by some additional information called a lifetime that say how long this borrow is lasting for. And so from the compiler's point of view, every time you have a shared reference, there's a lifetime going on under the hood. But as a programmer, you don't really want to think so concretely about lifetimes. You want to just say, oh, I'm taking a borrow here, I'm sending out a borrow here. Compiler, you just work it out, right? So in particular, when we write the signature at the top, the way that's actually interpreted is there's some lifetime, which I'll take as a parameter, tick A, and you're going to give me a borrow that's valid for that lifetime, right? But we didn't have to explicitly write that parameterization. This is sometimes called a form of polymorphism, right? We didn't have to write that explicitly. The compiler sort of interprets the notation we wrote at the top as shorthand for the thing on the bottom. Now that alone is maybe not so surprising, but we push this a little farther than you might have seen before. So you can have signatures with multiple borrows floating around, and then it's not so obvious how to connect up the various lifetimes. But we worked out, basically by gathering data from a large corpus of real code, what the common rules are. And it turns out that there are a set of rules that cover 97% of the cases and allow you to avoid ever writing this explicit tick A notation. So here we're saying if you take a borrow in and you say you're returning a borrow, you're almost certainly referring to the same lifetime in both cases. Okay, so these are like very syntactic details. If you were making a lambda calculus model of what's going on here, you would not talk about this at all, most likely. You wouldn't be thinking about this. But these kinds of details make an enormous difference to the usability of the language and actually getting it accepted and adopted in industry, right? I'm going to skip over this just for the sake of time. Sorry, skip, running a bit behind. Right, so in general, this elision that I showed you is just one of a large number of relatively superficial details that go into the borrow system in Rust. Right, so I'll just mention a few here. There's something called the borrow checker, which basically tracks what loans are active at a certain time. That's a very algorithmic kind of thing. Again, if you're making a semantic model of this, you probably would ignore this altogether. Notation that introduces temporaries behind the scene, deciding sort of when ownership is being passed by default versus when things are copied, and so on and so forth. All of these things are surface level details that it's very easy to brush under the rug. But my large point here is getting Rust accepted, right? This Rust is sort of taking this idea of substructural types, which has been very productive in academic research, but has made very little headway, in industry. It's trying to make it palatable. It's trying to make it usable at scale in industry. And a key to doing that is sweating these details at the surface level, putting them all together to give programmers a very comfortable ergonomic experience, right? So that's one big difference between doing sort of narrow, more theoretical research in academia and what it takes to actually put a language together that's going to have a practical success. Okay, second story. So another important feature for Rust is something called the trait system. I'm going to give you a quick tour. Traits are interfaces, essentially. If you know Haskell type classes, they're very, very similar. So I'll just walk through the notation real quick here. Here I'm defining an interface for printing some kind of value. So the trait itself is called print. Inside the trait, you can list some number of functions or methods, which are just functions that have a self argument. And I'm saying ampersand self, which means I'm taking a borrow of self to print. Don't worry if those details are not making sense to you. It's not too important. Okay, so then after I've defined this kind of interface to a type, I can go implement it for various types that can support that behavior, right? So I'm going to say how I want to print, so impl print for U64. So that's an unsigned 64-bit number, and I give some code to print it out. I can likewise do something for characters. One thing that's kind of interesting about this, in contrast to interfaces in languages like Java or Scala, is you can actually implement these interfaces for types you didn't define, right? So you can add new traits of your own, and then apply them to existing libraries, and that's a powerful way to glue things together. That's also a feature that type classes have in Haskell. So there's one other kind of interesting thing related to that, which is you can say, I can print any vector as long as its elements are printable, right? So you can have these kinds of conditional implementations. This is, again, very inspired from Haskell's type classes and used all over the place in Rust, okay? So these details aren't super important. I just wanted to give you a flavor of the trait system. Okay, so why am I talking about traits? Well, traits are an example where we have somewhat abandoned the principle of orthogonality, which feels like a very heretical thing to say. So let me explain what I mean by that. So traits can be used in two pretty different ways in Rust. One is you can have a function that uses them sort of as what we call in industry generics, aka parametric polymorphism. So basically it just says, give my function some type t. I don't know what that type is, but it must satisfy the print interface. And when I have that constraint, then I'm able to call print on that type. Okay, that's great. In the generics use, we get static dispatch. And so what I mean by that is the compiler actually specializes every such function at compile time. So if I call a function that's parameterized over print with U64, I get a copy of that function specialized to U64. If I call it with characters, I get a version that's specialized to characters. And that's really great for optimizations because everything is fully concrete. We know the precise size of all the types and so on. That kind of thing works fine when you are dealing with one-off types or things like vectors of U64, so where you have a container with elements of all the same types. What it doesn't give you is heterogeneous collections, right? So if I want a vector that contains things with different types all mixed together, but I know that all of them satisfy print, the sort of parametric polymorphism or generics approach doesn't give you that, right? That's something that's a somewhat more object-oriented kind of idea. So it turns out that we also use traits to support this kind of object-like behavior. And that gives you dynamic dispatch. So basically, you get some extra storage here that tells you at runtime what function to call. So instead of at compile time specializing everything, you just have one function that has this vtable on the side that tells you how to call it. Again, details here aren't super important for the overall point. Right, so, okay, so what's the connection with orthogonality? So I said before, orthogonality is sort of about not coupling together ideas, different kinds of ideas into a single feature, right? So the principle, which is like motherhood and apple pie to PL people, is, what you should do instead is provide a whole bunch of small features which are all independent and which can be composed together in arbitrary ways, right? That's how we do good design, or so I thought, right? So one interesting thing, actually Rust mostly does follow this orthogonal design. I think it is a good principle overall, but there's actually been a pretty important downside in practice, which is if you follow this principle a lot, your language can become very difficult to teach. And what I mean by that is, basically, we have a lot of different small features in Rust which combine beautifully, but that means to understand anything that you want to do in Rust, you have to understand a large number of these features and how they work together, right? And so it's made it very, very difficult to write books on Rust and teach tutorials on Rust. We have to sit very carefully and tease out, an order of these features to teach so that you can actually do useful things all the way along the way. So there are real downsides. And so in general, one, as a sort of counterpoint when you're doing design for a real language, you end up looking for these kinds of opportunities to do a little bit of coupling, to sort of get more bang for your buck. So I think traits are a good example of this in Rust. The generics case and the object case, if you're analyzing that theoretically, you probably want to understand those as two very different features. And there are good reasons for that. So like the object case in Rust, for example, has limitations that the generics case doesn't have. So there are these weird corners in language. Things don't fit together quite as nice as they would if they were, totally separated features. But they fit together well enough. So there are certain things you can't do, certain limitations here and there. But by and large, you can move between these two modes of thinking, and the semantics is pretty smooth, right? And traits also do a number of other things in Rust. I won't go into the details on those. But the idea is basically for the sake of teaching and productivity in the language, we really want to get a lot of bang for our buck when we introduce a new concept. So we look for these opportunities for one concept to do a lot of work for us in the language, right? But it's a careful balance to make sure you don't get too many of these corners. Okay, let's see. So last story, now I'm getting pretty short on time, so I'm going to sort of blow through this a little more quickly. So I want to close by talking about sort of an aspect of language design that never even really occurred to me when I was working in academia, which is API evolution. So Rust was pretty interesting to work on before the 1.0 days, because basically we broke the language and the standard library on a daily basis. So we had this passionate community who every day they'd load up a new version of the compiler and fix all their code to work with the new changes. And that was great. But at some point, right, if you actually want to make a successful language, you have to ship a 1.0 and start making backwards compatibility promises. So that was a big part of the work I first did when I was at Mozilla, sort of organizing this process. And at some point, it occurred to me, well, hold on. Okay, if we're going to start making these promises, what does that actually mean for the standard library? What kinds of changes are we going to be allowed to make to the APIs there? And how does that interact with language design? Okay, and so you might imagine, in general, the story here should be pretty simple. For example, you should always be able to add new functions or new types to a module, right? There's no problem there. Well, so actually there is. So here's just a simple example where we have a submodule. It today defines one struct, foo. We're using it in some other module that's defining a struct bar. And we're doing something interesting. When we import the module, we're using this nice little convenience, a glob import that says, give me all the public aspects of that module, right? So today this works fine. Tomorrow, if that module adds a bar struct, we have a clash, right? We're defining bar, we're importing bar. And this is resolvable in lots of ways. So for example, you can have a semantics for star that says, well, if you have something local, it shadows the thing you're importing or whatever. But it's something to think about, and it's something that's easy to miss. And actually, if you're thinking about models of languages, chances are you wouldn't have even included star in the first place. You wouldn't have even thought of this kind of issue, right? There are so many examples of this, right? We went systematically through every language feature and said, what if we added an API here? What would happen, right? Unfortunately, I think for the sake of time, I'm going to have to skip this one. But basically, there are cases in the trait system as well where adding new impls of a trait can actually break existing code. Okay, so what we ended up doing is something I think pretty interesting and somewhat theoretically appealing. So we had these cases that could sometimes cause breakage in code that was using these libraries, and we really wanted to allow them. It wasn't always possible to change the language feature to rule out the breakage. So we came up with a rule, which I think of as an elaboration rule. And basically what this says is, if there was a way to change the client code by disambiguating it somehow, maybe by being more explicit about the imports or adding a type annotation or something like that, and if that disambiguation could have been written before, that is, it works in both versions of the upstream library, so you can straddle different versions, that kind of change is A-OK. And this has actually been really crucial to evolving the standard library in Rust. There have been a number of cases here where, technically speaking, we could break your code, but there's a small disambiguation you could write that lets you straddle versions and makes the breakage pretty tolerable, right? And so that's where we drew the line. But there's been a lot of interesting work as we've laid out this rule, making some changes to language features to support this well. So I'd love to talk offline about that. There are lots of interesting examples, right? And so here, the insight is API evolution is really important in practice. It's not something I personally ever really thought about when I was doing more academic design, and it's something I'm not aware of any work at the sort of calculus level that talks about this kind of thing. But I think there's actually a lot of interesting research that we could be doing here. Okay, so let me quickly wind down, right? So I've sort of framed this talk as models versus reality, which might put you in the mindset of, are we talking about scientific method here? Well, sometimes, right? Sometimes we do use models to understand something that already exists out in the real world, like object-oriented programming is a thing, and there was a line of work to analyze it in terms of the lambda calculus to sort of break it down into a simpler model. So that is sometimes the way we go. I think often it's about abstracting away from details so that you can get a really clear picture of a particular feature. But just like abstractions in code, sometimes these these models we're building, they need refactoring after they encounter reality, right? People talk about code smells. Sometimes there are model smells, right? And I think that's why it's really important to have a dialogue between people who are doing pure theory and people who are trying to put these ideas into practice to make sure that the two aren't diverging too much and getting too smelly. I sort of already mentioned clarity. So on the reality side, just a few final thoughts about, from my experience, the biggest difference, it's not surprising, right? Anybody in industry says the big difference is scale. You're operating with huge teams, you're operating with lots of money, you're building big things, right? And in the setting of a language, the scale is you're not focusing on a single feature, you're trying to put together a lot of features into a coherent whole. And that introduces a lot of concerns that you miss when you're just doing pure research on a particular feature. And one aspect of that is design takes on a greater role than just understanding, right? So when we're developing models, it's sometimes about design, it's often about understanding. But when you're developing a whole language, making a design that's sort of globally coherent is really important. And as I gave some examples, the details here, even at the surface syntax level, really matter a lot in practice. Finally, there are more constraints to take into account when you're actually building a real language. You really have to think about the learning curve, where things like orthogonality can actually get you into trouble. You have to think about ergonomics. How does the language feel to use, right? And also things like API evolution. Right, so bottom line, I mean, this is not a talk that's meant to say models are bad or not useful. On the contrary, every time I'm doing design in Rust, I am thinking in terms of the kinds of models that academics develop. It's an incredibly useful tool for exploring the design space. But you have to apply those models in a wise way, and sometimes you have to bend the rules. And that takes some time to learn. Cool. All right, I'm going to stop now. Thanks.